We're good.
Okay, so the lab you're gonna do today, we're gonna actually end up doing 3 labs that involve springs throughout the course of your esteemed AP Physics career. So the very first one that you did, way back when you were very much physics novices, and we were just learning how physics was done, and we put force on the y-axis and we put elongation on this axis because force was the independent variable, and we put more and more force on there, and I said, oh, to get this force, take the mass times 9.8 meters per second squared, even though you really didn't know what 9.8 meters per second squared was, okay? And you plotted the points and you said, ooh, yay for physics, okay? So this second time, now we're gonna look at it from an energy perspective. The third time you do this after Christmas, when we get into harmonic motion, then we're going to look at how energy changes form as this thing oscillates and period and a whole bunch of other stuff. So here's the drill. The first thing you're going to need to do is put these masses on there. So help me if you ask me how to calculate the weight column, I'm just going to shoot you. Okay? And then you need the elongation.
Now's our chance.
No, I do not know. I swear to God I will. And not a jury of my peers will convict me. Okay? So you're going to need some rings. So what you want to do is set this ring. This just makes it a little bit easier. So now, on the lab picture, it's going to show you to use like a hook at the top. Don't do that, mainly because of the fact that the hooks don't line up with the middle of the rings. So that's why I don't want you to use a hook. Put a rod through the top or a pencil or something, and then use that to suspend the top of the spring. So what you want to do is have this second ring down where the bottom of that ring is level with the bottom of the spring, okay? Because that's going to establish our equilibrium position. So once you get that done, like for example, you're going to take a 500 gram mass, and you're going to hook that up, and you're going to measure the elongation. So what you need to do is measure precisely. You can measure to the nearest. If your measuring device is going to have the whole number of centimeters, so you're going to know the tenths and you can estimate the hundredths. So you're going to measure from the bottom of this ring to the bottom of that spring. There's going to be your point, there's going to be your elongation. You're going to plot these points. So once you get that done, then you're going to come in here and you're going to have some points here, here, here. And you are going to draw a line of best fit, okay? A line of best fit. When you find the slope of the line, the points that you pick have to be on the line of best fit, okay? That's the whole point of drawing the line of best fit. Now, Cohen, you pay attention to this since you tend to neglect things that have an asterisk. So there's an asterisk here at the bottom of the column, okay? Ooh, woo, okay? So what you're going to do with this, that's going to be the elongation that's associated with the 1.5 kilograms, not 1.5 newtons, 1.5 kilograms. So you're going to come out here, you're going to have a certain elongation. We're going to establish that as the base point, okay? So, somebody take 1.5 kilograms times 9.8.
14.7 newtons.
14.7 newtons, okay? That's what we're going to use as our baseline value. So you're going to have this point and you're going to draw that line straight up. Now, listen to me. You're going to write down where it crosses the line of best fit. If that happens to be the exact data point that corresponds with that, great. Odds are it's not, but it has been known to happen. Okay? So you're gonna, listen to me, this is gonna be, it's later on, this isn't important now, but it's gonna be later on when you start to do some calculations. So that's why I have this asterisk. You're gonna go out here to the 14.7 mark, draw a line straight up. Where it intersects the line of best fit, you're gonna write down those data points, 14.7 newtons and however many meters that is, okay? Where it crosses the line of best fit, okay? Not necessarily the data point that's associated with it. Okay. So in terms of data collection, this is easy peasy, hang the masses, get the points, boom, there you go. Now, the next part that you're going to do is over here on page 2. So you're going to take 1.2 kilograms, and this is where you need the other rings. So 1, 2, buckle my shoe,
3, 4.
out the door.
1, 2.
Okay. Now, this is where the other rings start to come into effect. So, just have these rings up here. Don't worry about where they are right now. Just kind of have them up here like this. So, what you want to do is have this, and you want to take a C-clamp and hold this down. I forgot to bring one up here. So, because otherwise this thing tends to tip over. So what you're going to do is you're going to make this thing oscillate like this, right? Now, when you do that, this is why you have to adjust that position so it oscillates right in the middle of the rings. So this second ring down is your equilibrium. That's the unstretched length of the spring, okay? Now, this one, the second ring down, that's where it's going to be at the top of the oscillation. This ring is going to be where it's at the bottom of the oscillation. Now, that's a little bit tough to do because of the fact that you're watching it, but it's got to be pretty close. And the other thing that happens is that this thing loses some energy as it oscillates. You have some air resistance. The particles that make up the spring are being stretched and put back. That generates heat. Now, it isn't like, wow, my hands are cold. I'll wrap my hands around the spring and I'll warm them up. No, okay? But anytime you, on an atomic level, you have particles move past each other, they don't like it. It generates heat. So there's a little bit of thermal energy that's being created. Because if I let this thing oscillate long enough, what's it going to do?
Stop.
It's just going to stop, okay? Because of the fact that you're losing energy to wind resistance, you're losing energy to thermal energy, it's just never going to keep oscillating. Now, what you don't do, don't pull it down to the bottom ring like that and then let it go. Mainly because of the fact that if you do that, odds are it's not going to come back to that point. So just get it oscillating like this, okay? And then adjust the rings. Now, let's talk about what we're after. So, as that ring, or as that spring,
R is oscillating.
so here you are at the top, and then here you are at kind of the middle, and then here you are at the bottom. There's 3 types of energy that are involved in this. What are the 3 types?
Kinetic.
Colin, what's one of them?
Kinetic,
Kinetic. Why?
because there's motion.
Because there's motion. Okay? So it's oscillating back and forth like this. Does the kinetic energy, as it oscillates, ever go to 0?
Yes.
Preston,
Yes.
when?
After it's bounced enough times.
No. Even as it oscillates, right now, is the kinetic energy ever going to 0?
Yes.
Why?
When it stops.
2?
Potential.
No. Listen to your friend.
And it changes direction.
We're going to change its direction, right? Because the velocity has to go to zero, it has to slow down, stop, and speed back up.
Danny's lost. Reset.
So up at the top, your kinetic energy is going to equal what?
0.
0. At the bottom, what's your kinetic energy going to equal?
0.
0.
Infinity.
So if it's 0 at the top and it's 0 at the bottom, where do you think the kinetic energy is at its maximum?
In the middle. Exact middle.
In the middle. This is when you have your maximum kinetic energy, because this is when you have your maximum velocity. Okay? Later on, you'll see how you can calculate that. Okay? Cool. Got that going. See, I told you it tips over. Now, little counter torque over here. So, that's one type, kinetic energy. That's always changing because the velocity is always changing. Well, Stanley, what's another type of energy?
Potential. UG.
UG?
UG.
How do you calculate UG, Will Stanley?
MGH.
Does that value change?
Yes.
Why?
Because the distance between it and the ground changes.
Yeah. So as this oscillates, we're changing UG because of the fact that we are changing the height. Okay? So UG is going to change. Dapshan, what's the third type of energy that we're going to have? Us, which is going to be 1/2 K.
X.
So when is us at its maximum? Top or bottom?
Bottom.
Bottom. Why?
Because the X is the most.
Okay, that's when you have your biggest elongation, right? Well, Stanley, when is your UG at a maximum?
At the top.
Why?
Because that's the greatest height.
Yeah, that's at its greatest height, right? So imagine that you have a 3-container system. You have an UG container, you have a kinetic energy container, and you have an US container. So what's happening is that now this is like a 3-way siphon, and you're always changing them going back and forth. Now, here's the deal. So on the front of this lab, there is a diagram
Nuh-uh.
that shows you where you get X1, where you get X2, and where you get H. So, let me clarify this. So this is based upon this oscillating, right? So X1 is the distance from here to here. So don't feel like, oh, why do you have that? Because imagine this. Leave the fact that it's oscillating out of it. And I said, hey, how much energy do you store in stretching that spring from here to here? Oh, you need the K value and you need how far it stretches, okay? So all that's giving me is how much energy I store at the spring when it's at the top of the oscillation, okay? Now, from here down to here, that's going to be X2, okay? So that's going to be how much energy I store from taking it at its equilibrium point all the way down to the bottom of the oscillation, okay? So I've got US1 here, I've got US2 here, okay? And the difference between those two is how much the potential energy is going to change. Cool with that? Okay. Now, Will's value of height. So that height value is going to be how much that changes from the bottom of the oscillation to the top of the oscillation. So you're going to have 3 measurements, X1, X2, and height. So over here on page 2, that's where you've got these columns, X1, X2, and the height is just the difference between X2 and X1. Cool with that, okay? So the first thing you're going to do is you're going to make this oscillate with a fairly small, what we call amplitude. Amplitude is how much it moves out of its equilibrium position. So you're just going to have something like this, boom, make it oscillate, not a big deal. That's going to be trial 1. Trial 2, you're going to keep this, but then you're going to try and make even like a bigger oscillation, okay? Now, as that oscillation gets bigger, let's not go to the extremes, what's going to happen to the value of your x's.
Become greater,
They become greater. So what's gonna happen to your us?
become greater.
It's gonna be bigger. What's gonna happen to your h value?
Big.
It's gonna get bigger, right? Okay. Now, your third trial, you're gonna put on 1.5 kilograms. So then on that one, you're gonna take this one off, put on a 1.5, make it oscillate.
A lot or a little?
Huh?
A lot or a little?
Medium,
A relatively
okay? Medium.
decent amount.
So,
As much
in
as I
terms
will.
of data, that's all the data that you need. Okay, that's it. The devil is in the details in terms of your calculations. Now, on here, page 2, okay? I don't need to see all four calculations for all 3 trials. I just want to see a complete set of calculations for trial 1. So here, you're going to show me how do you calculate the energy, potential energy stored in gravity when it's at point 1. Now, obviously to do that, you have to have the slope of the line. If you don't have the slope of the line, you can't find the value of us. Now, when I say show the work, I don't mean, oh, I'm just going to write down 1/2 kx squared. Showing the work does not mean writing down the formula. Okay? I want to see the numbers. You're going to show me how you calculated these values. So you're going to have us 1, us 2. Then you're going to have your change in us, which oddly enough is going to be U2 minus U1, okay? Not a big deal. All you have to do is subtract. And then the UG value is just going to be MGH, okay? So here I want to see these calculations for trial 1. If you want to write in the calculations for trials 2 and 3, great, you don't have to. But at least down here, show me, hey, I know how to do these calculations. That's what you got going on. Then you got a bunch of questions to answer. So when you get to question number 7, okay? When you get to actually 6, 7, and 9. So using the graph of the weight and elongation, determine the area between the line of best fit and the x-axis using the x and y coordinates found on page 1. So when you do question number 6, if you go back up to this graph, this is where you're going to need this value. So the base of that triangle is going to be 14.7 newtons. That's going to be the same for everybody. Okay? Everybody's going to have the same base of 14.7. The variable is going to be where it crosses the line of best fit. Will's might even be different than Cohen's. Okay?
No.
Depending upon how Will draws his line of best fit versus how Cohen draws his line of best fit. Okay? So this is why I said, go out there to that 14.7 Newton mark, draw a line straight up, see where it crosses the line of best fit. That's what you're going to use as the basis to find the area of the triangle. Okay? Everybody cool with that? Now, when you get to question number 7, using the equation relating work to storing potential energy in the spring, find the work done in stretching the spring to the maximum elongation. Okay? So on number 7, work equals us, which equals 1/2 kx squared. So on number 7, you're just going to use 1/2 kx squared. And how far did it take to stretch? This has nothing to do with oscillating in the springs. Okay? Number 7 has nothing to do with oscillating in the springs. It's just, hey, we stretched it to 1.5 meters. What's our elongation? And then when you get to number 9, on number 9 where I said using work equals Fx, where x is the average force, okay? Do not make this difficult. On this one, just find like the medium elongation. In other words, just come across here. And because you can make this difficult, and you can add them all together and do that, but it's just gonna be a god-awful amount of work. Just find the maximum elongation, call it 0, and that maximum elongation. Find the average between the 0 and the maximum elongation, and then do what?
Add them together and divide by 2.
Yeah.
Average it.
Yeah. So basically what I'm saying on number 9 is that, hey, if you were to just draw this as a horizontal line at half your average elongation, find the area underneath there. And then you've got some questions to answer on, some multiple choice questions to go work off of. Anyway,
B, D,
I am done.
C.
You're on your own. All right, well,